All right. So we're going to talk about what makes one acid stronger than another acid. Um, all you really need to know going into this part of the lecture, okay, is that the definitions of acids and the definitions of bases. So an acid is something that gives away H plus. All right. So a stronger acid is one that's more generous in terms of giving away H plus. And then a base is something that takes H plus. So a stronger base that takes away H plus. It's stronger at actually grabbing H plus. And one other thing that you're going to want to know is that we have an actual measurement. It's an equilibrium constant that we measure to measure just how strong an acid is or just how strong a base is. And so Ka is what we call our measurement of acid strength, and Kb is our measurement of base strength. So So the first three parts of this lecture go into some of those details. What we're looking at now is what is it about the structure of one molecule that makes it a stronger acid or a stronger base? All right. So let's think in general terms. What are some features we might expect something to have if it's going to be a strong acid? Well, remember, an acid has to have H that it's willing to give away as H plus. So an acid we usually write as HA. And to be an acid, it's going to split into H plus and A minus. All right. So if A minus is more stable, that will mean the acid will be stronger. All right. A minus has a negative charge, so anything that's going to stabilize that negative charge is going to make the acid stronger. What else? All right, electronegativity. I mean, that's one factor that might make A minus more stable is electronegativity. So usually more electronegativity of A will stabilize the negative charge. Another way to look at it in my original acid molecule, what kind of partial charge would we expect there to be on H? Positive. So anything that makes H more partially positive is going to make the acid stronger. And again, we could say electronegativity is going to be a contributing factor there. And there's one other factor that you might not think of right away, but we need to break the HA bond, right? So having a weaker HA bond is going to be something that makes the acid more acidic. So those are general factors, and now we're going to look at specific situations. And the previous slide lists them really. The 4 things we're going to consider would be what atom is hydrogen bonded to. Electronegativity is going to be a factor there. Other nearby atoms in the molecule can have an effect on acidity. Formal charges in the molecule can definitely have an effect, and then resonance can definitely have an effect. All right. So we're going to apply these general principles to think about some specific situations. So first off, let's look at what atom the hydrogen is bonded to. That's probably the single most important effect. Be what atom it's bonded to. So compare these 3 things: NH3, H2O, HF. So focusing on the partial charge thing, if we were to put delta pluses on the hydrogens, where would we put the biggest delta plus? HF, because fluorine is more electronegative. So maybe this one's got a big delta plus, a big delta minus. Here it's going to be medium, and here it might be a smaller delta plus. This is lowercase delta, yeah. You might remember that from way back in the fall. We use these little lowercase deltas. So one way to think of this is like, okay, definitely HF should be the strongest acid of the 3 because it's got the biggest partial positive on hydrogen. H2O should be the second strongest, and H3 should be the weakest of the 3, based on the partial charges. We can also consider the stability of the conjugate base, the stability of A minus. So if we think about what this makes, if I take away H plus from NH3, what does it make? NH2 minus. If I take away H plus from water, it becomes OH minus. If I take away H plus from HF, it makes F minus. All right. Well, I just want to indicate which atom has the negative charge. If I, the question was, why did I put the minuses on the side. Maybe I'll actually write these as Lewis structures to make that more clear. So we could ask ourselves which one of these negative ions is the most stable of the negative ions. And the answer is F minus because it's not because it has 8 valence electrons. In fact, they all follow the octet rule. They all have 8 valence electrons. And it's not because fluoride's the only one not sharing any electrons, because sharing electrons is not inherently a bad thing. It's the same argument for why we made the delta pluses the way we did. If you're a negative charge, who would you rather live on? A more electronegative atom. So the F minus ion is more stable. So we have going left to right, increasing partial positive charge on the hydrogen. We have going left to right, increasingly stable anion after it loses H+. And the acid strength follows the same way. We have increasing acid strength that way. And this is true in general. When you look at the periodic table, if you have hydrogen bonded to an atom, as you go from left to right in the periodic table, the acid strength will get stronger. So NH3 is actually such a weak acid, we don't even consider it an acid at all. H2O is a very, very weak acid. HF is a, stronger acid than H2O. So as you go from left to right in the periodic table, acid strength increases. Just to give you numbers to go along with these, I said we use Ka as our measure of acid strength. For NH3, Ka is about 10 to the negative 35. For H2O, Ka is 10 to the negative 14. And for HF, Ka is on the order of 10 to the negative 4. So you can see there's like a big jump in acid strength for each of those. Many orders of magnitude. So if I asked you to compare H2S to HCl, which one would you expect to be a stronger acid? HCl, because Cl is further to the right in the periodic table. Good question. So the question is, I mentioned NH3 is not considered an acid. Anything with a Ka actually smaller than the Ka of water. So anything with a Ka smaller than 10 to the negative 14th, we don't consider to be an acid. Because you put it in water, and if water is a stronger acid than the thing you're adding, then that thing you're adding won't be an acid. So NH3, it turns out, can actually be a base in water. We'll talk about that in a couple minutes. But the question is that why the convention is to write NH3 instead of H3N? Probably. I mean, most of the time when you write the H's in front, those are acidic hydrogens. So you write H2O or HF or HCl or H2SO4. Those H's in front are considered to be acidic hydrogens, whereas in NH3, they're not acidic, so we don't write them in front. I don't want to say there's like a hard and fast rule that you have to write things that way, but that may be why the convention is to write NH3 instead of H3N. All right. So now I want you to make a prediction If you compare the strength of HF, HCl, HBr, HI, predict in your head which one's strongest, which one's weakest, and I want you to discuss at your table. Okay, who wants to share what their prediction was? Catherine. All right, prediction. HF is the strongest acid. Why? All right, fluorine's the most electronegative. So if we think in terms of partial charge, we'd again think big partial positive here, a little bit small. Let me try and make that smaller. 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 So biggest partial positive over here on HF, smallest on HI. So for the same reason as the last one, we'd predict HF would be the strongest among these. Well, funny thing happens. Let me give you the Ka values for these things. All right, so HF we said was about 10 to the negative fourth. HCl, 10 to the positive seventh. HBr, 10 to the positive eighth. HI, 10 to the positive 10th. What? All right. This is not a trend you would have predicted, right? And I made you predict to make this point. Turns out that electronegativity isn't the only thing going on here. There's another thing. Could it have to do with the bond strength? I mentioned bond strength for a reason. Now, we learned way back in the fall that to make a bond, two atoms have to have overlapping orbitals. And the more effective that orbital overlap is, the stronger the bond is. Now, the problem is orbitals overlap the most effectively when they have similar size. So, hydrogen, how big is its orbital? Really tiny. So, fluorine, also really tiny. Hydrogen and fluorine make a relatively strong bond. Chlorine now is this much bigger atom. That bond between chlorine and hydrogen is much weaker. There's not as good orbital overlap. So the bond gets weaker. Bromine is huge. Has a really hard time bonding to hydrogen. Iodine, even huger. So imagine a giant trying to hold a baby's hand. I just like that image in my head. But imagine a giant trying to hold a baby's hand. It's kind of hard because, you know, the baby's hand can just kind of slip right through the cracks in the giant's fingers. So the bond isn't as strong when the orbital size doesn't match up as well. So here we have increasing size. Which actually leads to decreasing bond strength. And again, we can consider what the conjugate bases are. What we call the conjugate bases after it's given away H plus. What does it become? Well, HF becomes F minus. HCl becomes Cl minus. HBr becomes Br minus. And HI becomes I minus. And here the size is also important. F minus is actually like, I don't know, maybe this tiny little dot there, tiny little circle there. Cl minus is going to be a bit bigger circle. Br minus is a bigger circle. I minus is this big old sphere. So one other way you can rationalize this is if you're a negative charge, that means a negative charge means there's kind of an excess of electrons there. How do electrons feel about each other? They want to stay away. Well, if you're in the fluoride ion, you don't have very far to roam. So they can't spread away from each other as much. In the chloride ion, they can spread away from each other a little bit more. In bromide, they can spread away even more. In iodide, they can spread away even more. So it turns out that even though electronegativity tells us otherwise, the negative charge being spread out actually helps stabilize it as well. So this is a general trend that you see. As you move down the periodic table, acid strength actually increases. So H2S would be stronger than H2O, and so forth. Yeah. So the question is, I had mentioned that similar orbital size is a factor in bond strength. So when we're considering HF versus HCl versus HBr versus HI, the HI has a much weaker bond than HF does. The question was, does that hold true for like iodine bonding to another iodine atom? So if you compare an II versus an IBr bond, I'm not exactly sure what the difference in energy would be between those two. Yeah, so I know that it works in general, like on a broad scale. If you're looking at the same atom bonded to other atoms of differing sizes, generally the bond with something of similar size is going to be the strongest. But there may be exceptions to that. And usually, I think, bonds between smaller atoms tend to be stronger than bonds between bigger atoms, partly because the shared electrons between two bigger atoms don't get to be as close to the two nuclei as they do when two smaller atoms bond. And so there's not as much of a stabilizing effect for the electrons. All right. So we've seen if you look at the atom that hydrogen is bonded to, we have a left to right periodic trend and we have an up and down periodic trend. So those are the two trends you want to know. Next thing we said we were going to look at is other nearby atoms. All right. So acetic acid and trifluoroacetic acid. Acetic acid is this. Actually, I'll draw out the CH3 group. And then trifluoroacetic acid. How do you think that's different? There'll be 3 fluorides over here instead of 3 hydrogens. All right. What might you predict about those? I mean, without predicting an acid strength, don't take too many logical steps. What's the key difference between having fluorine there versus hydrogen there? Partially positive and partially negative. So fluorine is very electronegative, so fluorine is doing what to electrons? Stealing, it's pulling them toward itself, right? You're pulling electrons this way. So then that carbon that has the 3 fluorines bonded to it is now like, oh man, all these electrons are getting pulled away from me. What's it going to turn around and do to the carbon next to it? It's going to start pulling those electrons toward it. It's like a tug of war, and those fluorines are essentially pulling electron density all towards the left side of that molecule. So if we're thinking about the partial positive charge on the hydrogen over here, what could we say about the partial positive on the hydrogen in acetic acid versus the partial positive on the hydrogen in trifluoroacetic acid? It's much more positive in which one? In trifluoric. Yeah, we've got a big partial positive over here. And over here we've got, still a decent partial positive. So our prediction is that which one should be a stronger acid? Trifluoroacetic acid. Yeah. Another way to think of it is, in this molecule, you've got a big partial positive over here on the carbon, which is going to help repel the positive on the hydrogen to make it easier for the positive on the hydrogen to get pulled away. Another way to think of it is to think about what happens after it loses H+. In which case, is that negative charge going to be more stable? Derek? Well, I'm just asking, these two structures up here, in which case is the negative charge more stable? In which case would the negative charge be less unhappy? Because anytime something has a charge, usually it's not totally happy. But in which case is the negative charge more stabilized? If you're a negative charge, what would you like to be near? Positive charge. So would you rather be on the trifluoroacetic acid where there's a partial positive charge? The partial positive there is on the C, yeah. Or would you rather be on just regular old acetic acid where there's no partial positive charge because there's no really electronegative atoms? The trifluoroacetic acid. So here, more stable. All right, our prediction is that acetic acid should be weaker, trifluoroacetic acid should be stronger. I like to point out that you always have information at your fingertips. So if we wanted to know whether our prediction's true, what should we do? All right, let's type in acetic acid. Acetic acid, let's go to Wikipedia. If anyone ever told you it was banned from school, they're crazy. All right. So one thing that I haven't taught you yet, but in the last lecture I did teach it. This thing here, pKa, this is the negative log of Ka. So 4.76, that means the Ka of this is 10 to the negative 4.76. So you want to remember that number, and we will then type in trifluoro. Ooh, fluoro. Trifluoroacetic acid. And we look and we find trifluoroacetic acid, pKa 0.23. So here the pKa is 10 to the negative 4.7. Here, oh, sorry, I meant Ka. And then the other one, Ka, is 10 to the negative 0.23. Which one of those is bigger? Second one. So we were right. So in general, our conclusion is that having more electronegative atoms around is going to make an acid stronger. I didn't leave myself space to write it. All right, let's compare nitric acid to nitrous acid. That would be HNO3 to HNO2. Based on what we just said, what does your instinct tell you? Which one should be more acidic? HNO3 has more oxygens. Oxygens more electronegative. I want you to take a moment and draw yourself a Lewis dot structure for each of these. All right, I want to start by pointing out a couple of the wrong answers you might have drawn. The most common wrong answer is this first one up here. And I totally get your logic. You're like HNO3, so I'm going to write H and then N and then 3 O's. What's wrong with it? Well, not everything, but what if I put in the formal charges? This would be +1, this would be minus, this would be minus, this would be minus. So This would be HNO3 2 minus, which doesn't exist. This second one that I drew down here, it violates one of the rules that we said you try and avoid bonding oxygen to other oxygens. Those are generally really weak bonds. So that one doesn't work. One thing I want you to know about these acids with oxygen, these oxyacids, the hydrogen is always bonded to the oxygens. So HNO3 should be connected that way. And then HNO2 should be connected that way. So now to fill out my Lewis dot structures, there's something missing from each of them. Well, it's true they're not alive. This is true. All right, I'm missing lone pairs, and I'm also missing formal charges, and I'm also missing pi bonds. Yeah. So this one here has got to have a pi bond. This one here has got to have a pi bond. And then formal charges. I have a negative here and a positive there. And nitric acid does have an alternate resonance structure. Let me see if I can squeeze it in. So the student question is, this orientation of the oxygen that the hydrogen's bonded to is bent. And would that spin around? And the answer is yes, it'll spin around. It does not affect the resonance, no. All right, so our instinct was having the oxygen there, having an extra oxygen would make the acid stronger. And if you think about it, if you take the hydrogen away and leave a negative charges like what kind of charges? Positive. So which one of these two looks like it would be more happy with a negative charge on it? HNO3, because it's got that positive formal charge on the nitrogen. So, yeah, nitric acid is stronger than nitrous acid. It goes along with our conclusion from the previous slide, which is having more electronegative atoms nearby makes an acid stronger. This one, again, I think this Ka is about 10 to the negative fourth, whereas this Ka is about, I don't know, 10 to the positive 10th or something. Really big. I do want to point out there are some acids that you're supposed to memorize. The strong acids. HNO3 is one of them. And going back a couple slides, HCl, HBr, and HI are also strong acids. So if you forget about the periodic trend, going top to bottom in the periodic table, but you have memorized that HCl, HBr, and HI are strong acids, And what's conspicuously not on that list? HF. Then you can remember, oh yeah, as you go down the periodic table, they get stronger because HF is not strong, and then the other three are. Yeah. What's your, the question is HAT. HAT is something you wear on your head, and no, the question is about what about HAT? So hydroastatic acid. Um, the thing is, astatine exists in such a small amount on the planet that you would never even have like a collection of atoms of astatine that would even be measurable, observable, or anything. So you can forget about any chemistry involving astatine because you're just never going to deal with it. Question is, why is it there on the periodic table? No, because the periodic table wants to be it's an exhaustive list of all the, elements that are in existence or that we can bring into existence. So HAT happens to be one of those that occurs naturally, but occurs naturally in a really, really tiny amount, and we can't do any chemistry with it. So it's really up there for the physicists, not so much for us. So, all right. Sam just had a question about something kind of cool, which is fluoroantimonic acid. So you can look up more information about this, but one of the strongest, if not the strongest acid known, you can make if you combine HF with antimony pentafluoride. So you have SbF5, and which looks like this. Little review of molecular shapes. It's got 5 electron domains, therefore it's trigonal bipyramid. If you combine that with HF, what happens is this antimony, for whatever reason, is really attractive to lone pairs, and so the fluorine just can't help itself and is like, you know what? That antimony looks so like electron starved. I'm going to share a lone pair with it. And it makes this. Now, when the fluorine shares its lone pair, now what kind of formal charge does it have? What's the formal charge on that fluorine here? Positive. All right. Now, fluorine with a positive formal charge says, "Ack." I don't know. Think of the Kathy comics. So it's really, really unhappy. So that just immediately is going to throw that H plus away. And so this fluoroantimonic acid is an extremely strong acid, and it will dump the extra H plus. Um, basically, that will give away its H plus to anything. It's a very, very generous H plus donor. So that's the story of. You can look up more information on what it is, what it's used for, whatever. But it's nasty, nasty, nasty acid. Yep. So the student question is, can you have the H plus being driven off of the molecule without there being a chemical reaction? And the answer is by definition, no. Because chemical reactions, we say, is when you form and break chemical bonds, right? So by definition, when something gives away H plus, it's breaking a chemical bond. So by definition, we'd call it a chemical reaction. All right, so we've looked at the effect of the atom that hydrogen is bonded to. We've looked at the effect of nearby atoms. Let's look at the effect of formal charges. Two names that are useful for you to know. Ammonia and ammonium. I know they sound very similar. And they sound very similar, especially if you have a little pause after you say ammonia and you tend to say because then you're like, ammonia, and then you don't know which one you're talking about. So you want to be clear. Who can tell me the formula for ammonia? NH3. Ooh, that was not a good N. And ammonium. NH4 plus. All right. So, what's the biggest difference? What's missing from one of my structures? A formal charge. On which one? Ammonium. There's a formal charge on nitrogen. So which of these do you think it's easier to take H plus away from? The one that already has a positive charge. You know, this is a pretty straightforward one, but positive formal charges, these make a molecule more acidic. If we were to compare two molecules and one of them had a positive, one of them had no formal charge and one of them was negative, what effect would a negative formal charge have? That'll make it less acidic. And the Ka values definitely bear that out. Ka value for ammonia is like 10 to the negative 35. Ammonium, it's like 10 to the negative 9. So big, big, big difference. And then there's one more, the effect of resonance. Yeah, resonance. We haven't talked about it in a while. But I do love me some resonance. If anyone takes organic chemistry with me next year, or if you take organic chemistry in the future, which y'all should, resonance is the one word that I say every single day in my organic chemistry class. So one word, one thing that comes up every single day. Like I teach a summer school class. Every single day of that class, we say the word resonance. It's that important. So ethanol. Ethanol is this. CH3, CH2OH. And then ethanoic acid also, ethanoic acid is just another word for acetic acid, which we have already talked about. I don't know why I chose to say ethanoic here. This is the official name, ethanoic, whereas the common name, no chemist would ever actually call it ethanoic acid. You'd call it acetic acid. But that, as we've seen, is this. All right. So here, I mean, what your first instinct is, we've added a more electronegative atom. We've added another oxygen. So what should that do to the acidity? Make it stronger. And it does. And it turns out it makes it even stronger than like if we just added a fluorine there. Yeah. And it's going to have to do with resonance. So let's think about what it looks like when I take the H plus away. Take the H plus away. This one now looks like this. This one looks like this. In the molecule on the left, my negative charge, basically sitting on one oxygen atom, right? What about the one on the right? Now there's going to be resonance because of the two oxygens. I can share that negative charge and draw an alternate resonance structure. That looks like this. All right. If you're a negative charge, would you rather be stuck in one place or would you rather be spread out? You're spread out. Remember, negative charge is an excess of electron density. So there's repulsion associated with electrons being confined. So the more they can spread out, the more stable. So in other words, this one is going to be more stable. So essentially the rule here is if the negative charge can be shared, that will stabilize the conjugate base, which will make the acid stronger. And if we look at the pKa's, or if we look up the Ka's, this one's about 10 to the negative 14. This one, I keep saying pKa. I don't mean to. This one, the K is about 10 to the negative 5. Question. Mm. Good question. So the question is, in a lot of these acids I've been drawing, there's lots of hydrogens on carbon, right? Here, there's hydrogens all over carbon. Uh, Here, there were hydrogens on carbon, and yet we didn't pull any of those off. It was always from the oxygen. Well, go back to rule number 1. Go back to looking at the atom that hydrogen's bonded to. As you go left to right in the periodic table, it becomes more and more acidic because of electronegativity. Hydrogens on carbon are almost never acidic. Um, you'll see a couple of cases, HCN. So there, the hydrogen bonded to carbon is somewhat acidic. But most of the time, hydrogen's bonded to carbon because carbon is not very electronegative at all. Most of the time, those are not going to be acidic. So the question is, what about HCF? Well, you can't have just HCF. You could have HCF3, which I guess that hydrogen might be somewhat acidic. But also that probably would be very poisonous. All right, so everything we've been saying about acid strength. Now, we want to flip it and look at base strength. So remember, base strength is how likely something is to go out and grab protons away from other things. So what were the trends? We saw that atoms further to the right in the periodic table were, when hydrogen is bonded to an atom further to the right, it's more acidic. So when you're looking to bond a hydrogen to an atom further to the left in the periodic table, that's going to be a more basic base. One thing I would, before I say that, an acid has to have H, right? And what gets left behind when you pull that H away? Electrons, a lone pair. So base has to have a lone pair. So really, we'll look at the atom with the lone pair. And if it's further to the left in the periodic table, that's going to make it more basic. So the reverse of the trend for acids. Acids, we said acid strength increases as you go to the right. We also said acid strength increases as you go down. So base strength will increase as you go up. So really, most common bases we're going to see are going to be bases that have a lone pair on nitrogen. You don't see lone pairs on carbon very often because those end up being such strong bases that it's very hard to form them. And then lone pairs on oxygen, they tend to not be as basic. So nitrogen is really the sweet spot. It's kind of up and to the left in the nonmetal section. Question? Yeah, so ammonia is basic. The question is ammonia basic? Anything with a lone pair on nitrogen is going to be somewhat basic, yeah, generally. Everything I'm talking about is to do with covalently bonded molecules. So we're not dealing with metals. So we're really restricted to this upper right of the periodic table. All right, so we look at the atom with a lone pair. We can look at electronegative atoms nearby. Electronegative atoms nearby make an acid more acidic. So what will they do to a base? Make it less basic. We looked at formal charge. So a positive formal charge will make something more acidic, so it'll make it but a negative formal charge will make something a stronger base. The simplest example of that is H2O, where oxygen is neutral. Is that basic? No, it's just water. It's just neutral. But if I give that oxygen a negative charge and make it OH minus, now that is basic. And then resonance is going to be a little more complicated. So here we said if resonance stabilizes the negative charge, that's going to make something a stronger acid. When something acts as a base and grabs a hydrogen, that's going to give it a positive charge. If you can stabilize that positive charge by resonance, it'll actually make it a stronger base. I had to really kind of think up a contrived example where that would be relevant for you guys anyway. So I don't want you to worry too much about resonance and base strength. So real quickly, try to identify the stronger base in each of these examples. Okay, first one, which is the stronger base? HS minus is a stronger base. Yes, because S is further up the periodic table. All right. Arsenate or arsenite? ASO4 minus or ASO3 minus? ASO3 minus. More electronegative atoms nearby. Makes for a weaker base. So having that extra oxygen is going to make oh, you know what? These were supposed to be 3 minus too. Oops. Now this last one's complicated. The explanation is going to involve resonance. So I don't want you to worry too much about it. But the key here is you want to look at what happens when you add hydrogen to each one. And I'll point out that if I add hydrogen to the first one, now there's an alternate resonance structure. So the positive formal charge actually gets shared between two atoms. In the second one, the positive formal charge is just stuck on one atom. So here, this first one, if you add a proton, its conjugate base will be more stable. So it actually turns out this first one is the stronger base. But like I said, that was kind of a contrived example that I had to come up with. That is an actual scenario, yeah. But not one that you really need to worry about at this level. The first one is a stronger base, yeah. All right, good. That just leaves this one last little part of the lecture that I can finish another time. Yes. You should not turn on your problem set. You should correct your problem set. So we've got the quiz tomorrow. And we've got X block right now. Who knows when we'll have another one?